meantime, we're going to hear from Dattani on robust AQC and spin systems.
Hello. Oh, is this one on? Hello? Yes. Good morning, everyone. I'm going to talk about robust AQC and spin systems. This is joint work with experimental collaborators. Li Jiaokai, the first person I've mentioned here, is in the audience right now. And this is a group at USTC in China. And on the Oxford side, Richard Tanburn and Toby Cathcart-Byrne, my students that graduated just this year, and Emil Okada, who's a third-year student, and Nathan Bryans, who's involved in early work. So I want to talk about doing something useful that classical computers cannot presently do yet. So for example, factoring RSA 230. The largest or the smallest RSA number that's not yet been factored is RSA 230, as far as I know. Last year, I said it was RSA 220, and Elizabeth was in the audience, and she said 5 days ago RSA 220 was factored. So, but this time I double-checked. RSA 220 took 7 years to factor. The previous RSA number factored before that took 5 years. So I hope RSA 230 isn't factored by a classical computer yet. Discovering the Ramsey number R55. Most of you maybe don't know or care about Ramsey numbers, but Paul Erdős, famous mathematician, said that if aliens came here and asked us for Ramsey number 55, we should get all the computers in the world, put them together, and try to calculate what Ramsey 55 is. If they ask for Ramsey 66, we should invest in military and attack the aliens, because there's no way we're going to be able to give them what they want. So Ramsey numbers are very difficult. The best classical algorithms scale double exponentially. So even if your quantum algorithm scales exponentially, that's still exponential speedup. So 5 is a huge number for Ramsey numbers. One thing we might want to do is the energy spectrum of a water molecule to within spectroscopic accuracy. There's a paper by a good friend of mine, Ryan Babouche, who's probably in the audience. Adiabatic simulation of quantum chemistry. That's one way that you might be able to use AQC to calculate energy levels of molecules. I think this is a very underappreciated paper. I'll talk more about it later. But why would we want, there's no laser pointer or anything like that, right? I'll just point with my finger maybe. And it's my fault for not bringing one. Oh yeah, okay. Perfect. Okay, yeah, so why would we want to calculate the energy spectrum of a water molecule to spectroscopic accuracy? We use spectroscopy to detect water on different planets. This was published in Nature Geoscience. I think geo means Earth, but this is about Mars. There's not yet Nature Martian Science, but maybe one day there will be. So this is the ExoMol project at UCL. That stands for exoplanet molecules. This is the Hytrin project at Harvard. On August 1st, I'm going to be going there for a one-year sabbatical, basically as a consultant on calculating energy levels spectra for molecules with very high accuracy. If you're not interested in exoplanets, for example, ExoMol, which is exoplanet molecules, if you're not interested in exoplanets or aliens or anything like that, you might be interested in humans. So the atmospheric chemistry experiment, which is based in Waterloo, which is my alma mater, this is spectroscopy of atmospheric molecules, understanding how the ozone layer breaks down, how it comes back, how CFCs decay, reactions in the atmosphere, all sorts of things like that. So what is needed to factor RSA 230, for example? We want to do something that a classical computer has never done before. So the answer is 5.5 billion qubits on a D-wave. If D-wave had arbitrary couplings, not just the chimera couplings, but arbitrary couplings, this could be reduced to 18,000 qubits. If we had a 4-local device with arbitrary couplings, this would be reduced to under 6,000 qubits. Multi-qubit interactions can be quite powerful in terms of if you want to reduce a multi-qubit interaction into 2 local interactions, you need a lot of auxiliary qubits for that. What is needed for finding a new Ramsey number? There's only 9 Ramsey numbers known, but if we wanted to find one that classical computers have not yet found, this is a list of Ramsey numbers that have not been found, except for R333, which has been found. But the rest of these have not yet been found. So this one, for example, needs 780 qubits. It needs 30,000 2-qubit interactions, 10,000 3-qubit interactions. Some of these numbers, you can see it needs 2,050,000 15 qubit interactions. Give me a quantum computer with that. 2 million 15 qubit interactions. We can reduce some of these. Deductions, if A, B, and C are all zeros and ones, what is C? I can dictate the answer to you, but then you won't learn anything. If you think about it, then you figure it out on your own and remember it for the rest of your life. What's C? A, B, and C are 0 or 1. Someone answered? It's 0 because we have 3 on the right side. We cannot possibly have 3 on the left. Here's a more complicated one. A plus B plus C equals 1. What deduction do you make from that? Oh, brilliant. So if A and B were both 1, the left side is too big. So any pair of these variables has to be 0. So this doesn't drop the number of qubits. We still don't know what A, B, and C are. They can be anything. But we can reduce multi-qubit interactions if we find a pattern like this. Notice A, B, C, D and A, B have a minimum. We can replace A, B, C, D with A, B everywhere in the Hamiltonian. What happens when we do this for the factorization problem, for example? We started with a big number. We wanted to factorize it using AQC. We start off with 100,000 multi-qubit interactions. The factorization problem starts as a quartic Hamiltonian, so it has 4-qubit interactions. We got rid of 94% of the 4-qubit interactions and 83% of the 3-qubit interactions for this particular problem without adding auxiliary qubits, without doing perturbative gadgets. I hate perturbative gadgets. I would much rather two-localize or quadratize a Hamiltonian without adding auxiliary qubits if possible. And the classical pre-processing time is 0. It's nothing compared to the time it would take to actually optimize this Hamiltonian. So this is our list of Ramsey numbers, which are unknown, the number of x-qubit interactions that we need to find all of these different Ramsey numbers. If we apply this scheme for reducing multi-qubit interactions using deductions, we call this Deduc-Reduc, then here we see for this Ramsey number, 20 million 7-qubit interactions completely eliminated. 30,000 12-qubit interactions completely eliminated. The classical pre-processing time is 0 compared to the time it takes to actually find the ground state. Then we can apply a whole host of different methods. This is a method that Neil Okada and Toby Cathcart-Byrne came up with. Recursive search-based reduction, then there's FGBZ, clique substitution, direct substitution, generalized roof duality. These are all methods that have been very popular in the image processing world, in computer science, in classical optimization of k-local problems. We can actually reduce this chart into this cute little chart over here. Are now the same. See over here, R33, 400 qubits, 2,003 qubit interactions. And you found the Ramsey number. Helmut, I gave you this Hamiltonian. Still for classical algorithms to find the ground state of this Hamiltonian. But R333 is actually known. If we wanted to know, for example, R103, 1,500 qubits, 9,000 3-qubit interactions. That sounds somewhat doable in the near future, isn't it? We already have 2,000 qubits. We just don't have 3-qubit interactions. However, there's one thing I hid from you. That's that there's 800 million 45-qubit interactions. So it's really tough. That's why it hasn't been possible to do this with classical algorithms yet. It might not be easy to do on quantum computers either. What else do I have to say here? R103. So if we were able to do this, that means discovering something we don't know. We don't know R103. The quantum computer has the potential to tell us something we do not know. What about quantum chemistry? We have this Hamiltonian. This is not H2O. It's not water. It's H2O without the O, just H2. This is from Ryan's paper that I showed you earlier. Only 4 qubits and 10 couplers. And you're done. You have the ground state energy of H2 at any point of the potential energy surface. But there's 4 local terms. They're non-stochastic. So the last talk, I think, was called Limitations of AQC. Here I have a slide. I didn't change it during the talk. This is what it was called before. Serious limitations in AQC devices. I think everyone knows most of these. I'm going to say them anyway. Available operators, we need ZZ and XX for a lot of problems, or ZZ and XZ. Usually we only have ZZ. We want K locality. I want 45 qubit interactions, or 9 qubit interactions, or something like that. D-Wave can only do 2 local. NMR can do 5 local. Connectivity, if 1 qubit can only interact with 6 other qubits, that's a limitation, which ideally we would be able to interact with anything. Coupling strengths, I don't know if this is still true. I don't have access to a 2000Q, but I think in earlier D-Wave machines, there was a limitation on the strength of the coupling to 2 digits of precision or something like that. Number of qubits, all 1 to 4 can all be fixed if we add auxiliary qubits. We can add tons and tons of auxiliary qubits and turn our 45 local problem into a 2 local problem. But doing that, we only have 2,000 physical qubits, for example, on the present-day D-Wave devices. The first D-Wave, I think, was 128 qubits. $10 million for 128 qubits. $100,000 each. I give you a house, you give me a qubit. Now, I give you a car, you give me a qubit. D-Wave machines are getting cheaper. They're getting cheap. NMR devices can do 12 qubits at the most. Full control, though, this is full universal gates on 12 qubits, and other than gate-based error correction or something like that, in AQC, the physical qubits are the same as the logical qubits with NMR. You don't need auxiliary qubits to localize a 4 local Hamiltonian. The spectral gap is also a problem. If you try to fix 1 to 4 by adding auxiliary qubits, you can also shrink the spectral gap. That's a nightmare, isn't it? This energy landscape manipulation technique, ELM is what we call it, can be used to widen the gap. Let me talk for a second about spin qubits. So spin qubits can do K-local stochastic Hamiltonians. These are 2 examples. We can do K equals 5, no problem. 5 local Hamiltonian, no problem at all. 2 local non-stochastic, no problem either. XX, Y, Z, Z, it's been done. It's been published, it's been done. K local and non-stochastic. Here's an example of a 4 local non-stochastic spin-based experiment. One may wonder why. Anyway, I don't have much to say about that. But this seems remarkable, doesn't it? 4 local, non-stochastic, done, easy. There must be a catch. Is this too good to be true? The answer is yes. It is too good to be true. All AQC implementations in spin systems to date used control pulses that cause the system to leave the ground state at some point. It's not truly adiabatic. There's one way we can mitigate this. If we reduce the probability of exciting into an excited state, making the gap bigger without changing the ground state that encodes the information that we want. This is called energy landscape manipulation, or ELM. So we came up with 2 different flavors of ELM. One of them is using deductions, Deduc-ELM. Here, we applied this to an integer factorization problem and got a 754% speed up. And I don't have a lot of time left, do I? So I'm going to go quickly. ELM with multiplicity, we got a 250% speed up there. How do we do this? Here we have a Hamiltonian, and here we have some constraint on the ground state. What deduction can we make here? There's some, yeah? New microphone? Perfect. Okay. So what deduction can we make over here? What happens if P2 and Q1 are both 1? The left side is too big, isn't it? So P2, Q1 and P1, Q2 have to be 0. That's necessary for the ground state. So we can add these terms to the Hamiltonian. We're not changing the ground state at all. We're adding 0 to the ground state. But the excited states are pushed away. If P2 and Q1 equals 1, we have an excited state. That doesn't satisfy the ground state condition. We're pushing away the excited states. So what if we don't have something like this? Some easy deduction we can make. We can find them using local searches. This is just 3 variables. We can easily do that. We've gone up to 200,000 variables like this. It doesn't take a long time on a classical computer. So we can really find a lot of deductions, really do a lot of energy landscape manipulation. Putting it all together, we can now do some spin-based experiments. This was submitted on 25th of June, 2017. And the first author, Li Jiaokai, that did a lot of the experiments, he's in the audience right now. So a typical NMR experiment, you'll see the system is exiting the ground state whenever we apply these control pulses to move the system along the adiabatic passage. Now we can do it with the ELM-transformed Hamiltonian. We can do it without such problems. Here's the pulses at the bottom. We can actually take snapshots of the ground state at 12 different points in time during the adiabatic passage. Using tomography, we can see the system is in the ground state the entire time. So why not just try adiabatically without ELM? What would happen if we tried to do the previous typical experiments without ELM? We have the fidelity, this is with ELM, we have the fidelity is close to 0.97 the whole time. It's pretty much in the ground state the whole time. You can see a delta of 0.001 at the end. The final ground state is, we have the final ground state quite certainly. And if we didn't use ELM, we have this. You have permission to laugh. This is 0.03. That's orders of magnitude worse. So scalability is the question everyone is going to be asking. We can do for local, we can do non-stochastic. What about scalability? The largest NMR quantum computation so far was with just 12 qubits. This paper in January 2017 by Ray LaFlamme's group, when I was at Waterloo as an undergrad, my Ray LaFlamme was my thesis supervisor. Here he says, our 12-qubit system beat a classical computer configured with 2.4 gigahertz CPU and 8 gigabytes memory. It must have costed a lot of money to get a computer with 8 gigabytes of memory. Last I checked, the History Museum is not selling their artifacts anymore. So, but if any of you have access to a computer with 8 gigabytes of memory, I would like to apply for CPU time on it so that I can claim quantum supremacy over the best, or the 8 gigabytes classical computer. I'm running out of time, so I have the last slide here. Everything mentioned in this talk is not limited to NMR. NMR is a cute method that we can use to test things. The first Deutsch-Jozsa algorithm was implemented with MLR, with NMR. The first Shor's algorithm was implemented with NMR. NMR is easy to test things, but identical techniques can be used for any spin system. For local is still easy, non-stochastic is still easy, NV centers, ion traps, gallium arsenide quantum dots, etc., 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 etc. So this is a paper by Zhao Kai Li, was the third author. This is a paper published in March 2017 where they used NV centers to do adiabatic quantum factorization. Again, the two limitations of NMR-based quantum computing, addressability and polarizability. In NMR, you can only address qubits with the Larmor frequencies. With NV centers, you have that, but you can also address qubits spatially. Likewise, with NMR, you have polarizability of 10 to the minus 5. With optical pumping, with NV centers, that can be improved by 5 orders of magnitude. So I think there is some promise to do spin-based AQC. Maybe not 2,000 qubits yet, but I hope that we can move towards that. And we can do 4 local, 5 local, non-stochastic, no problem. So with that, I'd like to thank you for the attention. Thank you to the organizers. Thank you to the chair. Thank you to the audience. Thank you, Elizabeth, for going easy on me this time. And thank you.
You make it sound like embedding is enough to get speed up, but of course that's not true, right?
I don't think I ever said speed up anywhere.
I think you said speed up, 754%.
Oh, but that wasn't embedding. That was just manipulating the energy landscape, knowing I know something about the ground state. P1, Q2 equals 0. I can add that to the Hamiltonian, push away the excited states.
So you don't expect any speed ups even though you can embed. Is that true?
There's nothing to do with embedding in energy landscape manipulation. You have the exact same embedding, but you manipulate the coupling strengths.
But if you don't expect speed ups, then why won't you do the same thing on your laptop?
We can use these methods for classical algorithms too, but the classical optimization algorithms don't necessarily benefit from the same thing. So increasing the spectral gap, for example, is not necessarily as important for classical algorithms as they are for quantum algorithms, for AQC. Same with the coupling strength, same with the density of states near the ground state.
So you're not saying that you're expecting any speed up, even though, I mean, when people say factorization, it's quantum factorization usually means one thing.
Yeah.
but that's not the one thing.
Well, yeah, classical factorization algorithms are still faster than AQC ones. We still have classical supremacy there.
Okay.
I agree with that. We still have classical supremacy for factorization.
Sounds
So
like there will be